Now we discussed the properties of an analytic function. So we have already seen some properties of an analytic function. So the first property is that the analytic function obey Cauchy-Riemann conditions. The real and imaginary parts of the analytic function obey Cauchy-Riemann conditions. We can also express this Cauchy-Riemann conditions in another form, and we have seen that it is given by df by dz star is equal to 0. So that means the analytic function is independent of z star. So and the second property is that purely real and purely imaginary functions are not analytic unless they are constants. So if a function is purely real or imaginary, either u or v is 0. So when it is purely real, v is 0 and dou v by dou x, dou v by dou y are all zeros. So dou u by dou x and dou u by dou y should be 0 according to Cauchy-Riemann, and this is possible if and only if the other part, if v is 0, u should be a constant so that the function is analytic. So the functions like f of z is equal to 5, f of z is equal to 3i, etc. are analytic, but f of z is equal to x square plus y square, f of z is equal to 3iy, etc. are not analytic. So that is the second property. So now the third property is that the real and imaginary parts of an analytic function are harmonic functions. That means if f is analytic, then u and v are harmonic. Harmonic means they satisfy Laplace's equation in 2 dimensions. So a function is called harmonic if the Laplacian of the function is 0. So if u and v are harmonic, then del square u is equal to 0 and del square v equal to 0. So we have to prove this. So this is a 2-dimensional Laplacian. That is del square u is dou square u by dou x square plus dou square u by dou y square. So we have to prove that this is equal to 0 so that the function is harmonic, so that the real part of the analytic function is harmonic. So for this we can write this as dou u by dou x as dou by dou x of dou u by dou x plus dou by dou y of dou u by dou y. So now we have to apply Cauchy-Riemann conditions for the functions in the parentheses. Okay, so we can have dou by dou x of dou u by dou x is equal to dou v by dou y and plus dou by dou y of dou u by dou y. Dou u by dou y is minus dou v by dou x. So we can write dou square v by dou x dou y, and there is a minus over here, dou square v by dou y dou x, and we know that the order of the differentiation is not important, so we can write this dou square v by dou y dou x as dou square v by dou x dou y. So this both terms are equal and opposite, so that is 0. So the del square u equal to 0. So this shows that u is a harmonic function. So similarly, please prove that del square v equal to 0. So this is an assignment for you. And generally, the theory of harmonic functions is called the potential theory. So here, so u is generally called the conjugate harmonic function of v, and v is called the conjugate harmonic function of u. Okay, and so that u plus iv is analytic. So if f or u plus iv is analytic, u and v should satisfy the harmonic equations or Laplace's equations in 2 dimensions. And the theory of harmonic functions is generally called potential theory. So now we discuss the fourth property. So that is, in any analytic function f which is equal to u plus iv, the family of curves given by u of xy equal to a constant and v of xy equal to another constant are orthogonal to each other. So consider an analytic function f is equal to u plus iv. So then u equal to constant give a set of curves. K1 in different values കൊടുക്കുമ്പോൾ different set of curves കിട്ടും. And v equal to constant gives another set of lines, and we can see that these two lines u equal to a constant k1 can be have different values, and v equal to another constant are orthogonal to each other. They are mutually perpendicular to each other. So suppose we have curves like this, they are mutually perpendicular to each other. അപ്പോൾ ഇതൊരു ഫാമിലി ഓഫ് കർവ് എന്ന് വിളിക്കാൻ കാരണം k1 1 ആകുമ്പോൾ നമുക്കൊരു കർവ് കിട്ടും, k1 2. അപ്പോൾ k1 ഡിഫറെൻറ്റ് വാല്യൂസ് കൊടുക്കുമ്പോൾ ഡിഫറെൻറ്റ് കർവ്സ് കിട്ടും. സോ ദി ഫാമിലി ഓഫ് കർവ്സ് വിച്ച് ആർ ഗിവൺ ബൈ u is equal to k1, and the family of curves which are given by v equal to k2 are mutually perpendicular to each other. So now we have to prove this. We know that u of xy equal to k1. So now we have to differentiate this expression with respect to x. Then we get dou u by dou x plus dou u by dou y into dy by dx. So this is a multivariable function. So its derivative with respect to x is given by dou u by dou x plus dou u by dou y into dy by dx. So, and k1 is a constant, its derivative is 0. So from this we can have dou u by dou y into dy by dx is equal to minus dou u by dou x. So dy by dx equal to minus dou u by dou x divided by dou u by dou y. So this is the slope m1 of the family of the curves u equal to k1. u equal to k1 എന്ന് പറയുന്ന എക്സ്പ്രഷനിലാണ് നമ്മൾ സ്റ്റാർട്ട് ചെയ്തത്. സോ അതിൻ്റെ കറസ്പോണ്ടിങ് സ്ലോപ്പാണ് ഈ dy by dx. അതിനെ നമ്മൾ m1 എന്ന് വിളിക്കുന്നു. This is the slope m1 of the family of curves of the expression u equal to k1. അപ്പോൾ u equal to k1 എന്ന് പറയുന്ന ഫാമിലി ഓഫ് കേർവ്സിൻ്റെ സ്ലോപ്പ് നമ്മൾ m1 എന്ന് റെപ്രസെന്റ് ചെയ്യുന്നു. ഓക്കെ, അപ്പൊ അതിന്റെ എല്ലാത്തിന്റെയും സ്ലോപ്സ് ഈക്വൽ ആയിരിക്കും. ഡിഫറെന്റ് ലൈൻസ് ആണെങ്കിൽ അതിന്റെ സ്ലോപ്സ് ഈക്വൽ ആയിരിക്കും. ഓക്കെ, കാരണം k1ന്റെ ഡെറിവേറ്റീവ് ഇവിടെ 0 ആവുന്നുണ്ട്. സോ വോട്ട് എവർ ബി ദി വാല്യൂ ഓഫ് k1, ദി സ്ലോപ്പ് ഇസ് സെയിം. സോ നൗ ടേക്ക് ദി സെക്കൻഡ് ഫാമിലി ഓഫ് കേർവ്സ് v equal to k2. v of xy equal to k2. Now differentiating with respect to x, we get dou v by dou x plus dou v by dou y into dy by dx equal to 0. അപ്പോൾ ഇവിടുന്ന് ഇതിൻ്റെ dy by dx കാണാം. dy by dx is equal to minus dou v by dou x divided by dou v by dou y. Okay, so that is the slope m2 of the family of curves v equal to k2. So this is m2. So we have another set of family of curves. So their slope is m2. All the slopes of this family are same, and it is denoted by the letter m2. So now we can find m1 into m2. So when two lines are orthogonal to each other, the product of their slopes should be +1. So m1 into m2 here is dou u by dou x by dou u by dou y into dou v by dou x by dou v by dou y. So we know that these two lines are analytic. So since they are analytic, they should obey Cauchy-Riemann conditions, and therefore dou u by dou x is equal to dou v by dou y. So dou u by dou x by dou v by dou y is 1 into, and dou v by dou x is minus dou u by dou y. So dou v by dou x divided by dou u by dou y is minus 1. So m1 into m2 is minus 1. So that is since so this is true because u and v are the real and imaginary parts of the analytic function. So they should obey Cauchy-Riemann. അപ്പോൾ എല്ലാ ഫംഗ്ഷൻസിനും കേസിലും ഈ എക്സ്പ്രഷൻ ട്രൂ ആവില്ല. ഈ ഫംഗ്ഷൻ അനാലിറ്റിക് ആണെങ്കിൽ മാത്രമേ ഈ എക്സ്പ്രഷൻ ട്രൂ ആവുള്ളൂ കേട്ടോ. സോ ഫോർ every analytic function uf is equal to u plus iv defines two families of curves. U of xy is equal to some constant k1 and v of xy is equal to constant. So these two families form an orthogonal system. So that means if u plus iv is an analytic function, the one family of curve u of xy equal to k1 must intersect the other family of the curve v of xy equal to k2 at right angles. So this is the fourth property of the analytic function. So we can summarize the properties of the analytic function. The first one is that they should obey the Cauchy-Riemann conditions, or we can see that an analytic function is a function of z alone and it is independent of the complex conjugate z star, or dou f by dou z star equal to 0. So the analytic function should be independent of z star. And അപ്പോൾ നമുക്ക് പെട്ടെന്ന് ഒരു ഫംഗ്ഷൻ അനാലിറ്റിക് ആണോ അല്ലയോ എന്ന് ചെക്ക് ചെയ്യാം. അപ്പോൾ സെറ്റ് സ്റ്റാറിന്റെ ഒരു ഫംഗ്ഷൻ ആണെങ്കിൽ നമുക്ക് നേരിട്ട് തന്നെ പറയാം ഇറ്റ്സ് നോട്ട് അനാലിറ്റിക്. ഓക്കെ. And the second property of the analytic functions is that the purely real and purely imaginary functions are not analytic unless they are constants. അപ്പോൾ കോൺസ്റ്റൻസ് അല്ലെങ്കിൽ നമുക്കൊരു പ്യുവർലി റിയൽ ഫംഗ്ഷൻ ഉണ്ട്, അത് അനാലിറ്റിക് ആയിരിക്കില്ല, നമുക്ക് പെട്ടെന്ന് പറയാൻ പറ്റും. ആൻഡ് പ്യുവർലി ഇമാജിനറി ഫംഗ്ഷൻ ഇസ് ഓൾസോ നോട്ട് അനാലിറ്റിക്. അത് നമ്പേഴ്സ് ആണെങ്കിൽ അത് അനാലിറ്റിക് ആണ്, അത് കോൺസ്റ്റൻസ് ആകുമ്പോൾ അത് അനാലിറ്റിക് ആണ്, പക്ഷെ അതൊരു ഫംഗ്ഷൻ ആകുമ്പോൾ അത് അനാലിറ്റിക് ആയിരിക്കില്ല. ഓക്കെ. ആൻഡ് ദി തേർഡ് പ്രോപ്പർട്ടി ഇസ് ദാറ്റ് the real and imaginary parts of the analytic function are harmonic. So that means u and v should satisfy the Laplace's equation in 2 dimension, or the 2-dimensional Laplacian of u and v are zeros, or we can say that they are harmonic. And u is the conjugate harmonic function of v is the conjugate harmonic function of u. And the fourth property is that in any analytic function f is equal to u plus iv, the family of the curve defined by u of xy equal to k1 and the family of the curve defined by v of xy equal to k2 are mutually orthogonal to each other. Okay. So these are the important properties of an analytic function. Okay. Thank you.